Good morning, everyone. We are now ready to start the last main idea on our section on derivatives, or our section on calculus, which is taking a step back and looking at something beyond the derivatives. So to kind of talk about calculus 1, we can kind of break this down into, there's a little algebra review, there's a little derivative, and this new thing, which we will eventually call integration. And that's really the course as it stands. And so today we're going to start our first topic on the concept of integration, namely the concept of a Riemann sum. So here's a picture for you. His name is Bernard Riemann. This procedure that I'm going to outline was very rigorously defined by him, but in no way he was not the first person to tackle this problem. He was the first person to really answer it in a conclusive, sort of what we call a rigorous way. But this idea has been around for a long time. In fact, let's go back to some of the earliest attempts to answer this question. So if you go back to the concept of even like the early Greek mathematicians, so the question that we're trying to answer. Question: what is the area, for example, of a circle? Okay, that's a question that we're trying to answer. And one of the ways that you might answer that is you might say, oh, pi r squared. But the question really becomes of how do you know this to be true? Versus, for a circle, we have this area. For a square, it's just the side lengths squared. And so for the circle, we have this constant pi. Now, I'm not going to try to define pi for you or try to talk about why it is. I'm just going to talk to you about a method, sometimes called the exhaustive method, or the method of exhaustion, or the execution of exhaustion, that early Greek philosophers are trying to use. So let's pretend that I know how to draw, and let's pretend that this is a perfect circle. Okay? So here is the fundamental challenge. Straight lines, when it comes to area, are good. Curves are bad. So, how do we find the area of, for example, a circle? Well, what you might do is you might put a triangle inside this circle. And a triangle with straight lines is something that you are at least calculatable its area. But you'll notice that it's not a great, no one would believe that the area of the triangle is going to be the area of the circle. So then we'll take a jump up and we'll do the area of a square. And hopefully you'll kind of agree that the square is taking up more space inside the circle. It's closer to the area of a circle. And we'll just keep this going forever. Here is, in green, a pentagon. We could go in orange, a hexagon. We add more and more shapes. We add more and more sides. Again, everything that we're doing involves straight lines, and we believe eventually, hint, limit, the area of the circle is found. That is something that has been an idea for a long, long time. We use simple shapes to approximate complex shapes. So we want to take this sort of method of exhaustion, and we want to talk about a very practical thing that we can start doing with our function. So for the record, this is the function y equals negative x squared plus 4. And I want to know the area under the curve, which is the area between the curve and the x-axis. So just to kind of do some sketching, all of this area is what I would like to know. Now, the first thing that you'll notice is that it is curved, which seems like a problem. So what we're going to do is we're going to introduce a more basic shape. So let's introduce the concept of our rectangles, our chosen simpler shape. So let's specifically say we're going to choose two rectangles to approximate this shape. And how can I do that? Well, here's what I'm going to do. I'm going to create a rectangle. And notice the right corner touches the graph. This is sometimes called a right-sided or a right-handed Riemann sum. And we'll talk later about what a left-handed one would look like. So here's my first rectangle. We'll take all this area. Now, do I know the area of a rectangle? Base times height. I can measure this distance is 2. And I can measure this distance because I know this right point touches the graph, whatever the evaluation of the graph is here. This is going to be a base of 2 times the height is specifically f of 0, which, plugging into this equation, 2 times 4, this has an area of 8. Okay, what about our next rectangle? Well, if we go out until the right-hand side touches it, here's our rectangle. It's actually pretty flat. This has an area of 8. This has an area of 0. So altogether, for two right-sided rectangles, the area under the curve is approximately 8 plus 0, or 8. That is my guesstimate, because it's an educated guess, not just a random number. I'm saying the area underneath the curve is about 8. Okay, what if we do the same curve, but now, let's say I want to use n equals 4 rectangles. So this is -2 to 2. I'm going to divide this into 4 notches. So here's a notch, here's a notch, here's a notch. So notice each of these bases where my rectangles are going to go, they're going to have a base of length 1. And one way that you can kind of figure this out is base is b minus a over n, where I like to call this a and this b. So this would be 2 minus -2 over 4. This is 4 over 4. And this is why my base equals 1. Okay, now let's still do some right-sided rectangles. Okay, so I move up and I make my first rectangle 1. I go to the right side, I move it up. I go across, I come down. Here's my second rectangle. I go up, I move across. Here's my third rectangle. And this one, kind of boring. We run into that same problem. Now, it's very important that you be able to justify to me that some of these rectangles are overestimates. Sorry, that's my phone playing an alarm. Man, it seems like it's constantly playing an alarm at this time. And I've turned them all off, I thought. These two rectangles represent overestimates because notice they include this area right here that I don't want to count. But these rectangles are underestimates, because they don't include areas that I would like to include. But notice, I have just as many overestimates as underestimates. So by including more sides, maybe I'll get a better result. So what's this area? This height is going to be f of -1. So taking a look at this is a height of 3. So this is 1 times 3 is 3. 1 times 4 is 4. 1 times 3 is 3. And 1 times 0 is 0. So adding them all together, all of the areas of our individual rectangles, this is 3 plus 4 plus 3 plus 0, or it's approximately 10. So we went from 8 to 10. Now let's do a lot more. And in fact, instead of doing 4, I'm going to choose n equals 8. So once again, 2 minus -2 over 8 is 1/2. That's where all of these rectangles are going to go. And you can see, hopefully, that all of these rectangles added together, I'm not getting as many overestimates. Or, sorry, what I should say is the amount I'm overestimating or underestimating in each of these seems to be going down. It seems to be a lot closer. Like this one, you have this giant overestimation and this giant underestimation. Here, we have a fairly large overestimation and an underestimation. But each of those over and underestimations seem like they're getting smaller. And that's the important idea, is that as long as I choose enough of these sections, I should be able to find these. So, speaking about each of these individually, I can set up a function to represent each of these. So, for example, R1 is going to be the base, which is always 1/2, times the right-handed side right here. This is happening at -1.5. And as a reminder, f of x is -x squared plus 4. So there's R1. R2 is 1/2 the base times the height, which is f of -1. R3 is 1/2 times f of -0.5. R4, 1/2 times f of 0, on and on and on until we get to R8, which is 1/2 times f of 2. And you can see it's going to go -1.5, -1, -0.50. There'll be a 0.5, a 1, a 1.5, and a 2. And if I add all of these areas together, I believe that it'll be closer than this smaller amount of rectangle or this smaller amount of rectangle. Okay, so that's really what we're trying to do with these Riemann sums. We want to answer something very complicated, namely, what is the area underneath these curves? And curves are not straight, so we approximate them using simpler rectangles. Now, I do also have the ability to write these in a very set way. So one thing that you can do is you can say the area will be, this is a Greek sigma. It stands for sum or addition. And we're going to add a bunch of things together. How many things? We'll start at 1 to 8, right? Because we had 8 things to add. So this is an index. We're going to index it from 1 to 8, and we're going to specifically multiply, we're going to specifically add all of the rectangles. Now, what are the rectangles? Well, it's going to be the index from 1 to 8 of the base times the height of each individual rectangle. Now, what's the base? Well, we happen to know that it's b minus a over n, which in this case is 8. And the height is specifically f of x sub I, where f of x sub I chooses, for the first one, it's negative 1.5. When I is 2, it's negative 1. When I is 3, it's negative 0.5. It represents the ith x value. Here's x1, x2, x3, x4, x5, x6, x7, and x8. So we're turning this problem of complex shapes into, admittedly, a harder algorithmic, there's lots more steps involved, but ultimately it is better because it's at least something. And we believe, and hopefully you can see why this is true, that as we add more and more rectangles, we'll be able to get a better and better idea of them. Okay? So that's the concept of Riemann sums. I just want to show you two more ideas in Riemann sums. I'm going to go back to n equals 4, but now I want to choose what are sometimes called left-sided or left-handed Riemann sums. So once again, we're going to divide the domain into 4 triangles, but now instead of the right edge of the rectangle touching it, I'm going to do the left edge. So there's a left one. Sorry, we go up on the left-hand side, and then we go over. We go up on the left-hand side, and then we go over. And we go up on the left-hand side, and then we go over. Okay, so here's R1, R2, R3, and R4. Left-sided, notice the left edges are changing them. Now, it just turns out for this specific function, it's not a meaningful difference. If you compare this one to this one, you might just see it as being flipped, and that's just a quirk of the specific function that I chose. But ultimately, the important thing is, I can choose the left-sided or the right-sided. It's always going to be, eventually, as long as I choose n large enough, it's eventually going to approximate it. So you could also imagine, what if we came in here and we did some more left-hand shenanigans? Again, it's the same concept that we've seen. So turning it into a couple more things. So these are the areas I don't want to include. And just like that, suddenly we've created a n equals 8 left-sided. The main point is not that left-sided or right-sided is better. You're going to see overestimates and underestimates in both. What is better is to use what is sometimes called the midpoint rule, or a midpoint Riemann sum, where let's, again, divide it into 4. So here's a rectangle, here's a rectangle, here will be a rectangle, and here will be a rectangle. And ultimately, what we want instead of choosing the left or the right-hand side, we're going to choose the midpoint directly in the middle. So every single rectangle is both an overestimate and an underestimate. And one benefit to using the midpoint rule is that on the surface, it's going to be a lot more accurate for a smaller number of rectangles. So if you are doing a finite number of rectangles, it's usually better to choose the midpoint rule because every single section has its overestimation and underestimation. So in the red, that's all of our overestimation, and in blue, that's all of our underestimation. So, concepts. Bernard Riemann really rigorously defined the idea that we can break down a complex shape into smaller rectangles, depending on what rule we choose. And as long as we have access to the function, we'll know the heights. And as long as we have access to a particular domain, we'll have access to the base. We multiply those bases and heights to get areas, and we add up all of those areas, and we say we have approximated the area under the curve. Now, what are we going to do with this? For that, you'll need to wait until the next video.